Have you ever wondered how to make a decision in an environment where the outcome of that decision is uncertain? This video is going to discuss how to use probabilities to make business decisions. Before we delve into that, we're going to discuss one of the foundational concepts of probability, and that is whether the numbers are discrete or continuous. So a discrete number, it has to be a whole number. So a discrete number, an example of a discrete number would be like if you were rolling the dice, you can only have 1 through 6. You can't have 1.2, you can't have 3.6, you can't have 4.8. You have to have, it's either going to be 1 through 6. There's going to be no decimals. So those are discrete because there's only certain values. A continuous variable would be a variable that could be anything from 1 to whatever. I mean, it could be anything from 1 to 10 or 1 to 20, or it would depend on what your n was in that case, but it could have literally any value with decimals and stuff. So because of that continuous nature, those have to be treated in a very different method when you are looking at probabilities. So what we're going to cover first tonight is a scenario where the values are discrete. So what we're going to do tonight is a custom problem that I made up. So here it is. So you are bidding on a project that will result in revenue of $300,000 if you win the bid. The cost to prepare the bid is $10,000. If you win the bid, it will cost you $225,000 in labor and material to complete the project. So what you want to do is calculate the range of probability of winning the bid that would make it worthwhile to actually prepare the bid. So we're going to plug our numbers in directly from the problem. So the cost of preparing the bid is $10,000. We don't want to do an equals there. Okay. I'm going to take out our equals. You only use equals with the formula. All right. Our cost of labor and materials is $225,000. Our potential revenue is $300,000. And now we've got to calculate our expected value if we win the bid. So our expected value is going to be the revenue that we would generate less the expenses, and that is both the expense of the labor and material and the expense of preparing the bid. All right, now we've got to calculate our expected value if we lose the bid. Now in that case, there would be no revenue generated and there would be no cost of labor and materials, but it would still cost us $10,000 in order to prepare the bid. Okay. All right, so now we've got to calculate what amounts to our EMV, our expected monetary value, given the odds. And we don't know the odds. We're going to use GoalSeek to find them out in a minute. All right, so let's fill in what we do know first. So that is that if we win the bid, we're going to make $65,000. So you can link, I'm linking cell C6 because that's where I have it calculated. And the profit if we lose is that we're going to lose $10,000. All right, now we've got to calculate the chance of winning that would make it worthwhile to prepare the bid. And so we're going to use GoalSeek for this. So we're going to let GoalSeek fill in our value here. But we've got to link losing in here somehow because the odds of winning and losing are related. So if you have a 40% chance of winning, then you have a 60% chance of losing. The losing is the inverse of the winning. But if you have a 70% chance of winning the bid, you'd only have a 30% chance of losing. So what we do is we do 1 minus, and then we do the chance of winning. Okay, so we're going to do 1 minus the chance of winning. And right now it's 100% because I don't have anything here. However, as soon as we use our GoalSeek, then it'll fill in the number there. All right, the next thing we've got to do is calculate our EMV of the project. EMV is expected monetary value. And so to calculate that, we do the sum product of the odds of winning and losing times the profit that we would make in either event. Okay, and this point, that is negative $10,000 because our odds of winning are 0 and our odds of losing are 100%. Obviously, if those were the case, that was the case, we wouldn't prepare the bid. But what we want to find out is at what point is it worthwhile to prepare the bid. So we're going to use our what if analysis, and within that we're going to use our GoalSeek. We want to set this cell where we have the sum product, which for me is E12, to a value of 0. And we want to do that by changing the chance of winning. Get on the right thing, okay? By changing the chance of winning, which is for me is cell B11. So I'm going to press OK. And So what we find out is that with a 13.33% chance of winning or less, then we wouldn't want to prepare the bid because we would end up losing money on it. So watch, if I change this down to 13%, now our expected monetary value is that we lose $250. However, if I raise it to 14%, now our expected monetary value is $500. So you would want to evaluate what you thought was the reasonable chance of winning the bid, and if it was above about 13 to 14%, it would probably be worthwhile to go ahead and prepare the bid. Now, I want to point out, because this gets confusing with EMV, that in no situation would you ever make $500 on this. You would either win and make $65,000, or you would lose and you would lose $10,000. What EMV does is give you a way to kind of make decisions under uncertainty. If you repeated this process 50 times, of those times, you're going to make money instead of lose money. Okay? If you want a better discussion or a more in-depth discussion of EMV, I'm going to provide a link for you to my video that discusses EMV. I designed it for my problem solving and decision making class, but it might help you too if you're struggling a little bit to understand the rationale of EMV. But again, to make this cell 0, the chance of winning was 13.33333 going into infinity, okay? And I didn't go into infinity enough. We could go back through to goal seek and get it, but you get the point. All right, so now let's talk about when we would use a binomial distribution versus when we would use a hypergeometric distribution. You would use a binomial distribution if there were a fixed number of identical trials. Say you were going to flip a coin 100 times. For each trial, there are only two possible outcomes of success, or two possible outcomes, either success or failure. So if you were going to flip a coin 100 times, and you were looking for how many times you got heads, we could call that success, versus how many times you got tails, that would be failure. There are only two possible outcomes here, okay? Heads or tails. The probability of P remains, or the probability of success, which is your P, remains the same for each trial. So if I flip heads on the last trial or the last 5 trials, it still doesn't change whether or not I would flip heads on the next trial. Still, the odds are still exactly 50-50. So that means that the trials are independent of one another, because what I've done already does not affect what will happen in future trials. Okay, and then the random y variable equals the number of successes observed by the trials. So hypergeometric is very similar in that there has to be a fixed number of trials, and there still can only be 2 possible outcomes. Here's where it's different. In a hypergeometric distribution, the probability of success does not remain the same for each trial. So for this one, instead of flipping a coin, imagine pulling out a marble from a bowl. Say we have 500 pink and purple marbles in honor of my little girl, who those are her 2 favorite colors. If I pull a pink marble this time, I am less likely to pull a pink marble the next time because there's less pink marbles in the bowl to pull from. So I could start out with 250 and 250 and be 50-50. And if I pulled a pink marble first, now my odds of picking a purple marble the next time would be slightly increased, and my odds of picking a pink marble the next time would slightly decrease, and that would change with every single marble that was picked because they're not replaced. So that means that the trials are dependent on each other. So that's how you know which one to use. If the trials are independent of each other, in other words, what happened before doesn't affect what happens next, it's binomial. If they are dependent on each other, then you would use the hypergeometric distribution. So let's look at some binomial problems. So these problems come directly from your textbook. You can follow along on page 515 of your Excel 2010 Data Analysis and Business Modeling textbook. So what we want to find out is the probability that 60 people, and exactly 60 people, will prefer Coke to Pepsi. Per your problem, you know that there is a 50-50 chance that people will prefer Coke to Pepsi, and we're going to do 100 trials. So what you want to do is do your binomial distribution, because the probability that person 1 likes Coke or Pepsi is not affected by the fact that person 2 wouldn't be affected by what person 1 liked. All right, so we are going to use the binomial distribution. Again, if you have a little bit of trouble with this, I always recommend that you do the insert function box instead of typing it in, because it gives you some hints on the bottom if you can't remember what to plug in. So I already have my binom dist up, and so I'm going to press OK. Our number that we're looking for here is 60. The number of trials that we're going to conduct is 100, and the probability that S will occur is 50. Okay, and cumulative. This can be the tricky part of this, and we've got to decide whether this is true or false. If we were looking for the probability that 60 or less all the way to 0 would prefer Coke to Pepsi, we would use true. So that would give us a value for literally anybody between 0 and 60 that preferred Pepsi. In this case, we want false because we are looking for the number, exactly the number of people that would prefer Pepsi. So the question is, what are the odds that exactly 60 people would prefer Pepsi? So that is going to be false. Okay, and you see that you have what amounts to basically an 11% chance. You've got the 0.0108, so we'd round that 8 up, and it'd be about 11%. So what we're going to do now is look at the probability that 40 to 60 people prefer Coke to Pepsi. So what we are still going to be using are binomial distributions, but now we've got to use 2 of them. So I'm going to go ahead and put it in like this. I'm just going to type it in instead of using the box. So we are looking for, first of all, we're going to calculate the probability that we get 60 or less. So 60 is the number of S, 100 is your trials, your probability is still 50, and in this case we want true because we are looking for the probability of 60 or less. Then we are going to subtract the probability of 40 to 60. I'm sorry, the probability of 40 or less wanting, preferring Coke to Pepsi. So again, we need the binom distribution. And in this case, our number, okay, this is where, again, it gets a little bit tricky. We can't just plug in 40 because then what we would actually be calculating is the probability of 41 through 60 because we'd be subtracting the probability of 40 through 0. So we actually need 39 here. So that's something you've got to think about. Out of 100 trials, probability is 0.5, and our cumulative probability is also true here. Oh, and I've missed a parentheses, so yes, I'm going to accept that contribution. And so what we have is 96.48, which is slightly different than it says in your textbook only because of rounding. All right, so now let's look at the probability 2 or fewer of 100 rails are defective. And so we're going to use our binomial distribution again. And in this case, we are looking for 2. And out of 100, our probability is of a defective rail is 0.03, and we are looking for it to be true because we are looking for 2 or less. So our probability that 2 or less rails is going to be defective is 41%. Actually, we could round that to 42%. So there's basically a 42% chance that the shipment's going to be accepted. So if you're good with math here, you can tell that that means that there is a roughly 58% chance that this shipment is not going to be accepted. Your company might want to do a little bit more in order to overcome that defective rail problem before it's actually shipped out. All right, so let's do real quick the probability that a flight is overbooked. Now, a flight's going to be overbooked if they have more than 100 people. Okay, so what we want to find out, and actually this is a 1 minus to make this work because it's going to be the inverse of the binomial distribution. So we're going to find out what the binomial distribution is going to find out. What are the chance of 100 or less? Okay, so we used 100. Now we're finding out 100 or less out of 105 trials with a 95% chance that it will happen, and the cumulative is true. And we want the inverse of that because we want to know what are the odds of having 101 through 105. And we find that that is 39%. All right, I'm going to have to cover the hypergeometric in a second video, so I hope that this has been helpful. As always, if you have any questions, you are welcome to email me or come by and see me during office hours. Thank you.